Yeah, I got a nice lecture for you today, and we'll really finish out the core topics of this course. Next week's course is kind of infill, kind of some extra tools and techniques, and maybe a few extra tricks and tips and things. Maybe debate what we should fill the time with. Maybe we'll go a little deeper. Maybe there's one more thing we could do in stochastic response regression. Maybe we could do that. I'll have to think about that. But we're coming along here covering the key fundamental learning objectives. We're really doing, I think we're good. We've really covered the fundamental things. We've kind of lived up to the product warranty here. So today we're gonna do, let me get the windows moving here. Here we go. Today we're gonna do something called the Poisson response model. Work on it in R, talk about model fitting and diagnostics, and then kind of bring all this together and kind of finish up here with some skills and a little look back at a previous data set, the Minnesota highway data set, and talk about what it really means, how we could look at that data set in different ways. To get started here, I'd like you all to grab this data set from Learn. If you go into the forelacing directory on Learn, and then there's data sets in there. If you would grab this data set from Learn, this is what I'm going to be using here. And it'd be really great if you can try to follow along and do this model on your own computer as I demonstrate it. And then I can take questions or whatever as we go here. But this is our data set for today. This is a data set of car accidents, road accidents. In Kentucky, we call these wrecks, and I mean officially too. So a lot of really bad wrecks here. But car accidents, and from these car accidents, we have statistics. This is for each year. This is data for each year, and we have data on how many people died, how many people were killed in car accidents. And we have injury data, and we have serious injury data. And I would assume, I don't know this for a fact, but I would assume that the serious injury data is part of the injured statistics. So there's injured, and then inside the injured, there is seriously injured. So there are essentially three response variables here. And then we have independent variables, the year, which is a time trend line, the number of cars registered, the amount of benzene that's been purchased, and the population. And why do you think benzene? Why do you think the amount of benzene purchased is a controlling variable here in the number of accidents? Why do you think that? Why do you think benzene's? Why is benzene on the data set here? Why is benzene a data point?
How do you understand the column petrol? Like, is it how much there's inside the car? Or what do you mean by this?
Or no, I actually, I'm not clear what the multiplier is, because I believe it's times 1,000. And I believe it's liters.
Okay.
My best guess.
It says underneath liters of benzene sold times 1,000.
I wrote that.
Yeah, okay.
So
my bad.
I'm guessing. I'm not actually positive, because when I do the math in my head.
But if that's if that's how it is, then it's because the more petrol that is bought, the more driving is happening. So
Right.
more kilometers drove.
Right. So if this is a data set, which it is, this is a data set that goes over like 30 years.
The problem is the car gets more gas efficient, so it's not really a data point you can use because a car in 76 will drive fewer kilometers per liter, where a car in now will drive a lot longer.
So there's interesting factor there. Now we'll see that we can use the data, but we'll see that, as you imagine, now we've got this other shape function going on where driving distance is not linear with the benzene over time. It's got a curve to it, right? Because the efficiency of the cars is changing over time. So there's a lot of complicating factors in there. But anyway, yeah, I wasn't, the cars, I'm pretty sure is times 1,000. That makes sense. Population's times 1,000. I know that for sure. But the petrol, if I do that in my head, every car then is, I'm still not clear in my head if I do the math. How many liters of petrol a typical car uses in a
Ste
year?
Steven,
Yeah.
it sounds like you have something in front of your mic. Like,
Let me check the mic here. Let's see if I got the right microphone set. Ah. Oh, and that means the music was no good either. Ah.
sounded a
much
little
better.
funny. Yeah, perfect.
Oh, yeah. You know what happens is when I snap my computer in and out of the dock, it doesn't automatically reset. Oh, that's interesting. Boy, that means I had another Zoom meeting today earlier, and that means they couldn't hear me either. And when and the other microphone, of course, is in the lid of the laptop. And when the laptop's closed, because it's in the dock, it doesn't work worth a damn. All right. Thank you. Well, okay. All right. That just means I'll have to play that tune again after the break. All right. So the petrol here, the multiplier on this, I'm not sure what the multiplier really should be. It's just a guess. Maybe it should be multiplied by 6, 10 to the 6. Maybe not 1,000, but it should be multiplied by 1,000,000. Because maybe if it's 1,000,000, I don't know. Yeah. So maybe if it's like each car burns 1,000 liters of petrol in a year, maybe that makes more sense. So maybe that, but it doesn't matter because it doesn't change. As far as running the regression model, it's irrelevant as long as the scale is still there. It's just my guess about the number, the 1,000 multiplier. And I don't use that when I actually put the data into, the software anyway. Excuse a little laziness here. I grabbed this slide from previous semester and it's in Danish, so we just switch here a little bit. But anyway, so we have this data, right? And so the data is not real valued, it's integer, it's integer data. And the argument given for this in some texts and in the previous course is something like, well, the numbers are integer and therefore we should use a Poisson regression. And that's not really a correct explanation. I don't like that explanation. I don't like it at all, actually. That's not really a good reason to say, well, the data is integer and therefore I'm going to do a Poisson regression. No, that's not right. That's not correct. It's a Poisson regression because the data is a random sample. It's a Poisson regression because the data that we have represents a process that we very clearly know is a random process, and that the specific one data point we took is itself random. And unlike, for example, some of the other data sets we've looked at, where the y variable is very plainly fixed, it's very plainly, it has a much more clear specific value. Whereas this process we're looking at here, well, there's a random component to it, and there are many processes, passengers arriving at a train station, machinery breakdowns, failures of transport equipment, failures, motor failures, dead batteries on cars. What is the probability that tomorrow morning there will be 20 cars in Copenhagen that have a dead battery? Right? It's random. It's not. Some days there'll be a lot of people with dead batteries. Other days there'll be a small number of people with dead batteries. And there are factors like the weather and temperature. But after you figure out all the weather and temperature and everything, it's still a random, right? The number of dead batteries on cars is still going to be kind of really random. And you may be thinking to yourself, well, what the hell does dead batteries have to do with transport study? But if you're Falck and you have insurance contracts, or truck and you have roadside assistance insurance contracts, you need to figure this out, because you need to estimate how many trucks you need, tow trucks you need to go out and do assistance calls to your customers. And that's a random number. And some days you get no calls, and other days you get a lot of calls, even though the temperature is the same and whatever else. And it's, it's a Poisson process. It's a random occurrence of events that is generated by a exponential inter-arrival between those events. And there are many, many examples of it. And so this accident data is a Poisson process. The probability that there are so many deaths or so many accidents in a particular time period is the same concept as, okay, what's the probability that there are so many dead batteries, that there are so many cars that have batteries that go flat in the middle of the night or in the middle of the day or in parking or whatever. It's the same kind of deal. And just a little reminder, queuing systems this is where we're talking about this concept of an arrival process, of a birth death process is the technical word for it. It is if you're really, really high tech, some of you guys, we're talking about a Markov process. We're talking about Markov chains and birth death processes. But anyway, so this accident data is a Poisson distribution very often, and very, very, very often, and can be shown mathematically very often to be a Poisson process. So what is that Poisson process mathematically? You can just Google this, right? Go to Wikipedia. You're going to get this exact same thing. And some of you probably maybe already knew this. So it's a mathematical process. It's a distribution. It has a single parameter, the average, the mean arrival process, and it can take all kinds of different shapes depending on the value of the mean. And it has a number, and it is a probability distribution that gives an answer in integers. And it is the probability that a fixed integer number of events will happen in a given period of time. And it can be shown, actually, if you're really nerdy, it can be shown mathematically. You can do this on a piece of paper with a pen. You can calculate this out. You can show precisely that that for a Poisson process with this formula on the screen here, you can show that the times in between the arrivals are exponentially distributed. So it is a fundamental relationship that a Poisson process is a process where the time between each arrival in the process is exponentially distributed. Yeah. So we have this thing here, and now we want to this is really just like the multinomial logit model from last week. Same idea. A lot of the stuff's the same, and we use some of the same goodness of fit statistics. So it's really all a very shared concept here. Sorry, somebody's at the door. Hi, yeah, you getting ready to move? Yeah, I just the interviews are meeting online. Den er mærkelig, at elektriker kom forbi uden aftale. All right. So yes. So this is just like the it's actually simpler. This is actually simpler than the multinomial logistic model from last week. And your text actually does have it first. It actually has, this is chapter 11, and then the multinomial logistic model is chapter 13. And the only reason I flipped it is because this course previously always flipped it. And so sometimes I'm like, I don't want to mess with something that someone else thinks was a success. Maybe I could have flipped it anyway, because the textbook goes in this order. But anyway, this is simpler than what we did last week. Same concept. We have on the left side, we have a random distribution, and we are trying to use the betas and the coefficients and the x to estimate the parameter of the random distribution that is driving the output. But then you look at this formula, as I commented here on the slide. You look at this formula and you might think, and we'll get back to this, we will come back to this, but you look at this formula and you say, why do we need all this stuff? Who cares? Why do we need this Poisson regression stuff? This looks easy. Why don't we already got tools to do this. Why don't we just throw this into the linear regression model? No, and we'll talk about that a little later. That's not appropriate. We don't want to do that. Because the answer we get is going to be a little different. The answer is going to be a little different. We're not interested in predicting a fixed value of y. We're interested in predicting the probability distribution of y. And also, I think another reason to argue about this is that in the traditional linear regression model that we learned earlier, we're basically assuming that the y response is normally distributed. And this is not normally distributed. Fundamentally, it's not. So that also is a failure of improper modeling assumption, improper way to do this. So let's go into this. Let's come a gang here, and here's the code that we're going to use. Actually, this slide I should have hidden. This is the old material, and I've got better slides. I forgot to hit hide on this. This is actually, the next slide is the code. Well, I mean, it's the same code. I didn't mean to keep that slide in the presentation. So here's our code, and I'll give you a moment. Go ahead and just start doing this. Go ahead and run this code. And I'm debating myself. I think I've got all the stuff on the slide, so I guess I'll take it a little easy. And I won't quite open up my R window and try to do this live at the moment, because I have it all. It's going to give me the same answer. It should, but I have all the output and the results I've got on the slides here, so I don't need to really. I guess it's not critical that I do it live, but I can if I have to. But go ahead and run this, and hopefully for all of you, this is no big deal. You type in this code, it works, you get the answers. And then we'll go to the next slide here and see the result. But go ahead and run this code, and I'm just mentally in my mind estimating how long it takes you to type it in and correct any mistakes and then see the answer. But we're using the GLM function here, the general linear model package, general linear model code, which is built in. I don't believe this is part of the standard library for R, so you don't need to install a new package for this one to run. And then it's important that you have this family statement that says family equals Poisson. And we're just going to look at killed as the output data. So I'm not including the injured or the seriously injured in here. And we'll see later that that's probably a smart decision. So, oh, and you can see that fun little tip at the bottom. You know, there's all kinds of little extra commands you can learn and things. And sometimes it's hard to know which ones will work and which ones won't. But you can see here that you could actually combine these two command lines into one command line and it'll just go and it'll just generate the whole thing. Not always clear when that works and when it doesn't. You just have to kind of try and see what happens. But anyway, so here's our answer. There's our fit result right there. And looking pretty good. Comments here. Petrol is not coming up very significant in this result here. Petrol is not so great. But we, at this moment on this screen, don't really have a clear way. There's nothing on here on the screen right now that immediately just says, hello, let me tell you how good this is. And that's a little bit, I actually had a little email correspondence with the textbook author. And his response was, well, these guys that program R are not really the kind of statistical guys that do this kind of research. And therefore, they never put this stuff into their software as a default setting. And he wasn't too excited about R. He actually said that, he said for this textbook and for the later chapters, which we don't get, thankfully, we don't get to in this class, so it's not a problem for us. But he said for chapters 16, 17, and 18, which we don't cover, it would essentially be impossible to use R to do those chapters, because he says the R software, the volunteers, the people out there volunteering and writing the R software, they just haven't, they're not into this area. It's not their big deal. It's not their excitement zone. And so they haven't developed the software to cover chapters 16, 17, and 18. So he said, you really can't use R when you get to the very end of the text. And he said, you have to use commercial software. You have to go back to SAS, or he was a big fan of something called NLogit, which I've never heard of, but he's a big fan of it. So that's good to know. Good to know. And lucky that we're not going to run into that problem, because chapter 14 is the long, and I don't even know if we'll get to chapter 14, maybe not, but chapter 14 is the furthest we would ever go in this course, I think. I don't think we would ever have the energy to go further. So it doesn't matter. So there's this. So now the question, so I've been talking away here, and hopefully you have this result on your screen and it's working fine. So the question is, how do we test this thing for goodness of fit? Now, in regular linear regression, you know, we have our R squared. We have our significance test for the whole model. So now we need some tools like that for this model. So here's what they are. Here's what they are. So for goodness of fit, these are the two workhorses here. These are the two workhorses. I'm trying to think of a Danish word for workhorse, but anyway, the likelihood ratio test and the McFadden statistic. These are the two big ones. These are the two key tools right here. And so, but we have to do a little typing and generate these manually, because there's no magic command that just makes them come out. You have to do it by hand. It's not that hard. It's still not that hard, but it's a little annoying that they're not just generated automatically. The likelihood ratio test. The likelihood ratio test is primarily about comparing two models. And so we compare a simple model and a more complicated model. And in the most basic structure, we compare our model to a zero model, to a null model. We compare our model to an empty model. And that statistic is a way of discussing whether our model is statistically significant or not. And in an advanced method, we would compare our model to an alternative model and then use the statistic to judge
Have we actually accomplished anything, or are we just waving our hands in the air and not doing anything? So we'll see both of those examples here. So first, let's do the basic method. And the basic method is going to be comparing our model to an empty model, to the null model. And the null model is going to be our data without any variables. Our data with just a random, with an intercept and a random component. That is the null model. That is a model that says, we don't know, just stuff just randomly happening. And then the statistic is here at the bottom of the screen. You can see this statistic right here, this chi-square. It's a chi-square distribution. Why is it a chi-square? Well, remember way back when we talked about chi-square as something we used for multiples, something we use for variance, because it's a multiple. And so we're going to use log likelihood. We're going to use the likelihood function here. And the likelihood function is a multiple. So we're comparing two sets of multiples. So this is a chi-square relationship. So here's that statistic. So this is the test statistic, a lot of S's and T's in that word, test statistic for the comparison. And on the left here is the null model, the restricted model, the null model. And on the right here is our model, the unrestricted model. And we're going to get this number. Let's just a little quick review here. Remember, this is from like 6 weeks ago. Remember the variance test and the chi-square, same idea. It's the same. You can't just run away from this. If you thought, oh, it's all done, I don't need to worry about that anymore. It's coming back. We're doing it again. So chi-square and multiples and critical value and p-value, we're doing that again. And drawing the picture, right? And where do we sit on this picture? And is it significant, not significant? Same deal all over again. Remember this. So here we go. So we have this likelihood ratio test. And our null hypothesis is that these two models are not different and we're wasting our time and it doesn't accomplish anything. And the alternative hypothesis, the Ho-Et hypothesis, is, hey, yeah, there's a difference. Yeah, they are different. And yeah, so that's what we're testing for. And then in the basic case, when we say they're not different, we're saying, hey, thanks for all the effort making the model, but it's worthless and you're not doing anything, right? As opposed to, hey, there is something going on here. Yeah, there's something, your model does have some value. So here's the code. And you can, if you have your R window still open, now you can just go ahead and do this, run this code, and I'll talk slowly as you do this. Run this code. You need to create this null fit model first and just hold on to it and keep it in the background for future reference. So create the null fit model. And then you calculate the test statistic here, and you just type this math into the line and hit return, and it generates the number. And here in this example, my test statistic is 1,809 right here. There's my test statistic right there. And then I'm curious to know, what is the critical value that I need to compare this to? And this is a command that will this is the same as Excel, where you just are typing in chi-square function in Excel. So you just type in chi-square at the 95% level, at the 95% boundary, and how many degrees of freedom. How many degrees of freedom is going to be the difference in the number of degrees of freedom between the unrestricted and the restricted model. And the degrees of freedom is going to be how many variables are you regressing in the function. So in this case, the unrestricted model has 5 variables. It has intercept and 4 x's, and the null model has just the intercept is 1. So the difference is 4. There's a 4 variable difference between those two. So that gives us our test statistic, 9.48. And then you can calculate the p-value here. If you just type in p chi-square and put in your test statistic and your degrees of freedom, and tell it that you're looking for the right side tail, not the left side tail. You want the right side tail, and it will give you the value. And in here, it's null, it's 0. And it's pretty obvious why it's 0 when we draw the picture. Draw the picture, guys. Got to draw the picture. You know, you can see that there, my artistic skill is not good enough to fully demonstrate the long distance between a critical value of 9.4 and a test statistic of 1,809. So there's a little bit of artistic license here in my drawing. Of course, obviously, the test statistic here is way far over, way out of sight on the diagram. And it's so far over that the chi-square distribution has nothing left over. It's just, you know, unmeasurable, unmeasurable probability for the p-value. But it's the same idea here. So we have shown that the stuff on the left here, this over here, this is the hypothesis null, right? Over here, we're saying there's no difference between the model and null. This is the ho null ho null area over here, and the hypothesis, alternative hypothesis, is over here in this shaded area. And then over in this area, we're saying, hey, there is a difference. There is a difference between these two guys. So that's how that one works. And that's pretty standard. So we know that this model is significant. And then the next thing we want to look at is this McFadden statistic, this McFadden row squared statistic. So on this one, it's, again, same kind of math as the likelihood ratio. So you're going to reuse some of the stuff you just calculated. Really quick and easy to do this. But it's very similar to the R squared and linear regression. A large value is a good thing, but not always. And throwing more variables into the regression inflates this value. So it's the same kind of deal as linear regression. You know, you have to be careful that you're not just puffing up your model to make the McFadden statistic get larger without actually adding value to the model. So there it is. And then you just, you know, tip, tap, tip on the keyboard, and there it is. And you just run that little equation, and there you go. So we have a McFadden statistic of 0.85. And so this value is between 0 and 1, just like R squared. So this is pretty good. It's pretty good. 0.85. Yeah, I like that. I like that a lot. So yeah, that's pretty good. And that, I think, the next thing to demo here, I'm looking at the clock, make sure we're doing just fine for time here. Yeah. All right. So now let's manipulate this a little bit. Here's the result we got for the first model for the Poisson regression. The petrol is not statistically significant. It's not really helping us here a little bit. So let's drop it. Let's drop it from the model and see what happens. So now we are comparing our model to an alternative model. So this is the advanced method of likelihood ratio test. So we do that, and rerun the model in R, and I'll talk slowly here, give you a chance to do that. So rerun that model, but create it, you know, I called it Poisson 2, but make Poisson 2, which has the model with the petrol taken out. So no petrol in that model. Take out the petrol. And of course, there won't be any accidents, because if there's no petrol, nobody can drive. And so there's no accidents, right? Ha ha ha. But anyway, take that out and you run that. And so now you have two models. You have the original Poisson fit model and you have this Poisson 2 model. And then you run the log likelihood ratio on this thing. And there you go. You've got 2.53. Now, the degrees of freedom are now different. And I know it says DF equals 4 over here on the right. Just ignore that. That's not the degrees of freedom of what we just calculated. It's kind of a weird software thing. This is the degrees of freedom. This is the degrees of freedom of the first term in the equation you just calculated. It's not really very useful. It's not very helpful. So ignore this blue degrees of freedom equals 4. That's just going to get you in trouble. The degrees of freedom is 1 because we dropped one variable. So we have changed the degrees of freedom by 1. So the degrees of freedom for this test is 1. So we run the chi-square to get the critical value for this 0.95 at 1 degree of freedom, and it's 3.8. And so now if you draw your picture, we have critical value of 3.8, and now we have a test statistic of 2.5 on this side of the diagram. And now we're in hypothesis null territory. Now we can say, wait a minute, these two models are not statistically different, which is a good thing. Because it says we can drop that variable and the results of the model don't really get worse. We can make the model one variable smaller, and yet it is almost as good as it was before. So there's really no reason to keep that variable. And that's a good thing, as we learned with linear regression before. And then we can run the McFadden here. So same kind of deal. I've typed in the null fit function up here on the screen, but actually it's the exact same one as we used before. So you can just reuse that null fit code. I probably took a coffee break and then came back and restarted my computer or something and then had to start over. But it's the same null fit as we had before. So nothing's changed there actually. So run the McFadden and it's 0.845. And before it was 0.8465. It's so trivial a difference, it's not worth it. It's just such a trivial difference. So it's a good thing. It says that, remember from linear regression, that all things being equal, the simpler model is better. If we can get good results with a smaller model that has fewer variables, we should do that. And here, there's really no reason to have this petrol variable in the model when it's statistically insignificant and the qualitative goodness of fit is essentially really not changed. It's really not improved. So this model where we drop the petrol is a better model. We can judge this, that this is a better model. So we would do that. So next on the agenda here, what time is it? Just a few more comments and then we'll take a break. So what if I do it again? What if I keep going? So I say to myself, hey, how about the population? It's statistically significant. So I might be causing some damage by doing this because it is statistically significant. But they all are the other three are also really statistically significant. So just for fun, let's just do it. Just for fun. So we dropped that one. We dropped the population. And then if you do that, and you do the math and run through all the tests, you suddenly discover that this was a bad idea. And you discover that the likelihood test statistic becomes 6.9. And this is, again, a 1 degree of freedom change. So our critical value has not changed. So we still have that critical value of 3.8, but now we have a test statistic that is 6.9. So now we're back over here on the right side. And that means that we do have a difference in these models. So that's not a good thing because we don't really want to do that. And then we look at the McFadden, and it goes down, not a lot, but it goes down more than just a trivial percentage. It goes down like 2 percentage points. And it's a small reduction. Maybe you could argue that population is also not necessary in the model, but it's not an insignificant change. It is a significant change. So I would probably argue that population should stay in the model. That would be my position. My position would be, but there could be some people that would really push this point and argue and say, no, let's take population out as well. Because without the population, now we have a really simple model that still has a McFadden that's up there at 0.84. But I would not do that. I would keep the population in there. I would keep it in. I think it would be a good idea to keep it in. And so then, let's see.
Even?
Yeah.
What does the McFadden actually show? That 0.84? What exactly does that number mean?
I can show you exactly what that means. It shows you, right? Yeah, it shows you that, so the likelihood function for the, let's see, how do I explain this? This is not the pure likelihood function. This is a log likelihood function. And basically the smaller it is, the better. And I don't have the actual full math for this LL parentheses beta function. I probably should look it up. It's probably in your text. But the gist of it is it's a likelihood calculation. It's a multiplier, and in this case, a smaller number is better. And so the LL0 is the null fit model, and it has a large value. So the better the fit, and in fact, your book says it in one of the paragraphs of text. It says that in a magical, beautiful world, the LL, the log likelihood function of the beta, when everything is absolutely perfect, the LL beta is 0. So when LL beta hits 0 in this theoretical, magical place, your model is so perfect that LL beta hits 0, then and then the LL0, the LL null is some big number, then this thing, so that fraction becomes 0, and then this thing goes to 1. So the larger the McFadden number, the smaller your log likelihood of beta, and the better that your fitted coefficients are precise and perfect in the way they predict the residuals. It's basically, I think it's actually a function of the residuals. I'd have to pull out the book and take a look one more time, but the log likelihood of the betas is effectively a picture of what the deviation on the residuals is. And so when the residual deviation between actual values of y and the fitted values of y, when the deviation between those two goes away, when they become the same, then this LL, this log likelihood of the beta coefficients goes to 0. And so that's represents a perfect fit, the most perfect model in the world possible. And so the higher the McFadden number gets, it's because this fraction, this relationship between the log likelihood of the fitted betas coefficients and the log likelihood of the null fit model, that ratio goes to 0, and then all you're left with is 1. So that's what's going on with that statistic. And so, and conversely, when the McFadden number gets really small, it's because your log likelihood of the beta coefficients is getting large, because it's.
Can you go back one, Stephen?
Yeah.
But on your, it says here, similar to linear regression R, larger value is better, but not always.
Yeah.
But won't it be if you have LL to the
This value I'm talking about, this value is better. The rho squared.
It will be closer to.
Sorry.
The closer to 1 it is, the better, right?
Right.
So that's also a larger value.
Right.
You were just saying that it had to be smaller.
No, this value, this one right here.
Aha, okay, good. That's
This
what I
value
misunderstood.
right here.
I'm
this is the log likelihood right here. This
okay,
one,
perfect. Yeah, okay.
Yeah.
I was talking about the McFadden, and you were just saying that the smaller was the better.
This is the McFadden. This is the log likelihood. And this is the log likelihood of the null model. So when this log likelihood of the beta coefficients goes to 0, this goes to 1. And this goes to 0 because this essentially goes to 0 because the residuals go to 0. This essentially goes to 0 because the residual fit becomes so perfect.
I understand now. Thank you.
Yeah, it just becomes so perfect that there's nothing left. And yeah, that's what's going on. So let's see here. We were here. We did that. We did that. We got to here. And one thing, and then we'll take a break. Yeah, we're ready for a break here. Oh no, let's take a break now. It's 10 minutes of. Come back at 2 o'clock. I'll set the little timer. Let's take a break now. I'll be right back. I can warm up my coffee. All righty, we're doing that. A little break. All right, be back. All right, welcome back from coffee break. So what is the significance of that song? That song is actually significant. What is the significance of that song? It's actually quite clearly linked to our lesson today. What is the significance of that song? How many of you even understood it? I mean, how clear is it where you could, I mean, it's Swedish. How much of it are you able to catch without, you know, straining too much? Yeah. What's this? I gotta pop this window open. Where is it? Come on. All right. Here we go. Yeah, significantly old. Come on. Are you able to understand the lyrics? I mean, I can catch a little bit of the lyrics. What is he saying? What is he saying in the lyrics?
A fast guy named Svensson. That was what I got from it.
Yeah, and he's got to do what? Hold the Hoya?
I didn't really listen to it quite focused.
Okay. So the chorus line is, hold the Hoya. Keep to the right. And did you notice the date on the record? 1967. So it's a Swedish song saying hold to the right in 1967. What's the significance of that?
Sweden were driving on the left side of the road before then.
Yeah. I thought it was very appropriate that we're looking at Swedish accident data. And September 3rd, 1967. September 3rd, 1967, the entire country of Sweden switched overnight from
But they
driving.
made daylight saving. They made that you had to have lights on all day, and that actually made it. That's the reason why we have lights on the car all day, is because Sweden, when they switched from left to right, they made the rule that you have to have your lights on your car at all times. So the accident rate actually dropped when they switched because of having the lights on actually helped the statistics a lot.
Yeah. I didn't know about the lights thing, but that makes sense. And do you think they argued that the lights had to be on to help with the change in the direction of the road? Was it a combination of, oh, we're going to switch to the road, and to make sure that we, are really aware that the guy coming toward me is on the correct side of the road, we want his headlights on, so we're really clear on this thing. And then you figure it was so successful, they just made it permanent. You think it was temporary originally, and then it was made permanent later?
I don't know exactly what Sweden's idea was, but Denmark adopted the rule because Sweden's accident rate after switching from right to left, but having the lights on, actually dropped.
Yeah.
So I think they said that the success rate of having lights on all day actually counterpointed what would have happened when you switch from right to left. So then Denmark made the same rule.
Yeah, that makes perfect sense to me. That makes perfect sense. But you can go on YouTube and Google and search this, and there's also other videos about the road switch, and it's just wild. I mean, it's just really wild. It's just because it's it was September, so it's still a relatively long day, a lot of sunlight. So they have film, of it was like 2 a.m. or something. They did it, and they have film of at the clock strikes and all the cars pull over and stop, and then they wait for some period of time, and then they pull out again and flip the side of the road, right? And at the same time, all these crews were running around. They had the new signs under bags, right, and the old signs. And when the time came to switch, all of these people, all these employees went out and took the bags off the signs and moved them to the other, it was crazy. But what was the other, anybody know, one more thing about the Swedish road change? What was another big impact of the Swedish road change on public transport, on public transit? Anybody know what the other big impact of that was?
Well, the trains still drive on the opposite side. They still drive on the left compared to the right in Denmark.
That's true. That's true. Because of the road change, major cities in Sweden decided to close their tram systems. The only cities that kept their tram systems were cities where the trams had a large, significant amount of track in private right-of-ways or in the center of the road. But a lot of the other tram systems decided that the cost of rearranging their tracks and rearranging the platforms, the boarding platforms, and rearranging all kinds of other things, they decided that the cost of that wasn't worth it. So when the road switch happened, a lot of major cities, Stockholm and Malmö, they closed their tram systems. They discontinued electric trams. So spårvagn. So a lot of fun stuff. All right, so next thing on this little test here. You know, I thought, okay, just for fun, what if I throw in the injured as an indicator variable? And yeah, no, it does not help. Throwing in the injured as an indicator variable, the injured variable is crazy insignificant. You can see it has a p-value of 0.85. That's pretty bad. And the likelihood ratio is a joke. That's not going anywhere. And the McFadden figure doesn't change. So injured is not a statistically valid predictor variable. It's probably heavily correlated. In fact, it is probably very heavily correlated with the death rate, with the number of people dying. But as a predictor, it's useless. It doesn't really tell you what's going on. So here's our discussion. This is going to be a pretty short lecture today, because it's not that hard, I don't think. I think this is nice way to finish out the content. But let's talk about this. Remember this highway data we started a long time ago, way back before Easter, like 6 weeks ago. We did this, maybe 5 weeks ago, but we did this Minnesota highway data. And we've been using this for regression modeling. But now that we know what we know about the Poisson process, and we know what we know about modeling things, the question is linear regression the correct tool for this Minnesota highway data? Take a minute to think about that. I'd like your opinion. What is your opinion? Is this Minnesota highway data? Should we do it with Poisson regression instead of the linear regression? What should we do about this? And yeah, I did start recording. Okay. I did start recording. What do you think?
I think it maybe would be interesting to see, because I can't quite remember how it was, this data set, but wasn't the graphs showing the normal distribution very far off to begin with.
Yeah.
So we could already see in the beginning that it wasn't the greatest fit. But
Yeah.
I'm not like we haven't done that much Poisson, so I'm not sure how it would look in a Poisson model instead.
Yeah.
But I could imagine it would be better, to be honest,
Why?
based on the fact that how far off it was from the normal distribution.
Okay.
At least
what
in
if
the
you
beginning,
didn't
we
know
have to
that?
modify it a lot to make it somewhat usable to a normal distribution.
But what if you didn't even know that? What if I hadn't done that model yet? What about, I mean, when we think about modeling, it's really important that we think about the fundamentals and think about the characteristics of what we're doing, right? So like, you know, I mean, if your girlfriend says she'd like something sweet to drink, you don't get a salt shaker and pour it in a glass of water and say, hey, try this and see what happens.
Oh, that's true. That's true. I
Right?
see what you mean.
You start with the fundamentals of like, well, wait a minute, I know that sugar is sweet. So that might be what I look at first.
Yeah, but that comes back to the fact that I don't really know Poisson, the model itself that well.
Well, we're talking, when we talk about the Poisson, we're talking about this events going by. We're talking about this flow of events. And that Minnesota highway data and, oh, there we go. Come on. That Minnesota highway data is traffic flow. It's cars going by.
So there's a big random factor involved in it.
There's a big random factor, but it's textbook, right? I mean, it's by definition a Poisson flow. And I apologize. What is it with people calling me when I'm teaching? Sorry about that, guys. It just seems I'm home alone. No one else is home, and all right. But so traffic flow is textbook definition of Poisson. It's a flow of events. It's a flow of things going by. It's the arrival pattern of cars. So just by definition, we might say this highway traffic data is Poisson. But the only exception to this is that the data we are getting in this Minnesota highway file is not the raw data. It is not the original unmodified data. It is data that has already been modified. How has it been modified? If you look at the slide, the description of the data, how has this data been modified? This is not the raw data. This is not this Excel spreadsheet is not the original recorded data from people going, or from the little counting boxes,
the little registration boxes out in the road. It is not that original data. It is different. How is it different from that data? What about you girls? I haven't heard from you guys in a long time. It's always these guys in the top of the list always talking. Are you not even there? Are you in the kitchen cooking something and just listening to this in the background? All right. Yeah, you know what I'm talking about. All right. Anyway, look at this. Look at this. Right? The data has been changed. The data has been changed. So this isn't the raw data. It says average annual. So they took the raw data, they've already boiled it down. They've already boiled it down. So they're not giving us the actual original data. They're giving us the average of the original data. So because this data has already been manipulated, it's now a little bit of a problem to throw this into our Poisson model because we have taken out some of the content. So it's, and I'm going to show this to you right now, but I'm just saying this is one of the reasons why we will see it was not actually wrong to do this data with the linear regression model because we don't actually have the original raw data. If we had the original raw data, then it would absolutely be wrong to do linear regression on this data. We should do Poisson regression. But because we don't have that data, we have melted out, we have boiled down some of the inherent knowledge of this data. And so the difference is not so great. And let me explain to you what's going on here. So here's our Poisson distribution, and up above here is this Poisson fitted regression. And that lambda up there is an average. That lambda is a statistical average. It is the mean of the distribution. So the data from the Minnesota highways is the mean, is the average. So the Minnesota highway data has already been transformed in such a way that it in some ways fits directly into this linear regression. And so it can kind of just fit in there. It kind of just goes. So let's try it. Let's just see some examples. This is from, 4 weeks ago or whatever. So this is the best fitted model linear regression for the highway data, for the Minnesota highway data. This is the best fitted linear regression. And it was very nice, and a very nice result, and a very nice, this is the best subsets regression, very nice fit model, no problem. And then if I kind of have the raw R output here in the next few slides. Here's the raw output. So now I run this again, and I do, this is the best subsets. Then this is the result of the best subsets. And then this is the, also still the best subsets. And then, oh, here we go. And then, oh, that's what it was. That's what that screen is. Okay, this one is the result of me transforming. I took the Minnesota highway data and I transformed it with a log function. I transformed the arrival, the car count from the raw car count to the log of the car count. And that's what this result is. So here's a comparison of those three scenarios. So the first one is from 4 weeks ago, our linear regression. Then I do it again, but this time with the AIC subsets, but this time I transform the Y data with a log function. And that's the formula I get right there. So when I say I transformed it with the Y function, when I say that, what I mean is I took the Minnesota highway data and I calculated this. That's what I mean when I said I transformed it. So if this is the Minnesota highway data right here, this lambda, that's the Minnesota highway data. I transform it log, I get this. And then I use that as my Y in the linear regression. And that is darn near, when you look at this formula, you say to yourself, ah, that's the same thing. Why don't I just do that? I don't need to do this Poisson stuff. I just transform the data linear log and run the linear regression and I'm done, right? No, it isn't. Let me show you why. It's not the same. Let me show you why. So here we go. So this was this up here. This is, from 4 weeks ago. Then this is the transformed. Now this, then down here, I go back to the original data from up here. So this is this data down here. Take this data, go down to the Poisson model, run that, and get a solution. And these two guys, they have the same structure of log Y equals beta X. They have that same structure. But what's different is the way the model is fitted. What's different is the way the model is fitted. And so if you compare these two, they are very similar. They have very similar, they're very close. These are very close, similar numbers here. They're very close. A lot of similarity. So we're getting similar results, but they're not the same. And the reason they're not the same, even though it looks like the formula would be the same, it's log Y equals beta X. Should be the same. It's not the same. Why is it not the same? Because of the way these things are fitted. Because of the way these things are fitted. The linear model is fitting based on ordinary least squares. See how good I am at drawing on here with ordinary least squares. It is fitting based on minimizing the square of the distances between the fitted line and the points. This guy down here is a likelihood function. This guy down here is a likelihood function of the random distribution. And it is looking for a different kind of fit. It is looking for a fit that says, I want a fit that maximizes the probability that these points actually came from this random distribution. So they are two different functions. They are two different tools. They are two different things that are calculating what the objective is. So even though both of these two bottom ones here, even though both of these, see, I gotta switch. Even though both of these are based on, both of them are based on this same idea of what the function looks like. They get different results because the way in which they find the values of these beta is different. And so they have a different answer. And then you have to go through an argument of which answer is correct. And the answer to that question is, what are you trying to do with this result? And in our case, we are trying to fit a random distribution that we can then predict the confidence of the performance of this system. And in that case, the Poisson is better for this accident data, and possibly might be a little better for the Minnesota highway data, but it would be absolutely best if we did it with the Minnesota highway, with the original raw Minnesota highway data, and not the log, not the mean Minnesota highway data, because we're losing information. So we're a little bit in the middle ground on the Minnesota highway data. And let me show you some more. So we got that. Here we go. This is the residual plots. So here are the residual plots. So this is our linear AIC subsets residual. You all remember this. Kind of looks like that. Kind of has this kind of shape like that going on. So now I do the transformation. So this is the second one. But so now I get a little nicer flow, but I still have a significant cone here. Now I have a significant cone here. And then I do the Poisson regression, and I look at the residual plot for that, which is, you have to be careful about this because the residual plot from a Poisson regression is not exactly the same information as the residual plot from these other two guys, but it's still, there's some comparable things here. And we look at this, and we have a little bit of a bump down here, but it's still pretty good. These are an outlier, that's an outlier, that's an outlier. Maybe I'll teach that next week. It might be interesting to know more information about these outliers that the regression, that the residual plot is showing us. Might be good for me to describe that in more detail. But you can see here that this residual plot from the Poisson regression looks really good. It's got a nice even distribution there. So is there a difference? Yes. But this would probably be a lot better if the data set was the original individual data points and not the average. If we had all of the original data points, we would get it would be a very different conversation. We would have a very different fit, and we would have a truly accurate model of what the flow on those roads was. When do we use each kind of tool? Well, one of the benefits of the linear regression model, one of the benefits of maybe doing this guy right here is our tools for analyzing cause and effect are much better on linear regression. So we do not have this for Poisson models. At least I'm not aware of it. I've poured through this textbook, and I've been, catching up on 15 years of missed experience with statistical software, and I haven't seen it. There is not the same power. We don't have the same power to generate subsets and models and descriptions of these Poisson regressions that we do for a linear regression. So, and the post-analysis tools are not the same. And so, so one of the benefits of sticking with the linear model is you just have so many more tools to work with. You have so many more ways to analyze the data. But I think there's a very strong argument that for the Minnesota highway data, if you can get the original data with the original measurements, this Poisson regression is in fact the correct model, is in fact the correct way to do it. So we're actually, it's a very short lecture today. We've come really far along. My my biggest concern is I hope that when you're watching me and doing this, that you are practicing with the R software as we go, because now is the time to ask questions about that if it's not working, because then it's much more difficult to help you later if you write to me by email and say, hey, it didn't work. You know, now is the time to make sure that works. But we're really done. It's a short lecture today. We're really done. And what I can show you, I do have a couple of questions for you. So next week, my hope is we'll cover some more diagnostics. I think I should spend a little time more on outlier analysis, the Hessian matrix, things like that. That would be good to cover. Those are good skills. I'm going to try to dig up a case study to talk about. Might be a little tricky, but I'll try to dig it up. But a question for you guys is that I think would be really good is, are you taking any other courses? Are you doing any projects in any other courses where these skills could be used? And if you are, I think it would be really great if you told me and said, you know, we're doing this in this other class and we have this data and, you know, we'd like to try this. So if you have something like that going on, I'd love to hear about it quickly, because it would be good for me to use next week's class to try to discuss or go over some possible applications of all these methods in maybe some of your other classes or projects or whatever. At the top. Yeah, Joel.
Jeg har lige et spørgsmål omkring det der med R-studio. Jeg får sådan der, når jeg prøvede at følge med tidligere, så fik jeg sådan en fejlnotation i forhold til det, vi skulle lave det der med log leak 0 fit, hvor man skulle sammenligne med den første.
Ja.
I vores min skærm.
Ja, let me skip.
Og jeg kan ikke dele min skærm.
Ja. Oh ja, du må gøre det.
Jeg kan ikke.
Ja, nu kan jeg.
Kan du se det?
Ja.
Det hernede, det skulle lave den her. Og nu ved jeg ikke, om jeg har skrevet noget forkert, for jeg prøvede flere gange, hvor jeg skrev det ordret, eller jeg tror i hvert fald, jeg skrev det ordret, i forhold til, hvad der står i PowerPointet. Jeg ved ikke, om nogen af andre har samme fejl.
Det siger rigtigt ud til mig, men det er årsag til, at jeg sagde tidligere, at jeg er lidt i tvivl om, hvis vi skal gå i gang med RStudio. Fordi det kunne være noget forskel mellem RStudio og det rigtige R-command-linje.
Ja.
Så hvis du bare installerer almindelig command-linje software og prøver det der.
Okay.
Det kunne være, at det er noget, RStudio er ikke tilfreds med.
Jeg tænker, måske der er nogle af jer andre, der er med, som har prøvet det på RStudio, hvor det virkede.
Så det her virker på noget.
Du mangler et parentes. Det er derfor, der...
Gør det?
Ja. Du har for mange startparenteser. Du har sat en ekstra parentes rundt om den sidste... Og så skal du have tilføjet den, du lige slettede først op i starten. Nej, den skal... så burde den være der. Hvis du sætter en parentes lige der, ja, så burde den være der. Og sletter den foran den anden. Ja, sletter den der, så burde den være der.
Du mangler en her, ikke?
Nej, der skal ikke være nogen. Jo, der skal være en ekstra, ja.
Ja, så det lykkes.
Så det er fint. Jamen så tak for det, Christian.
Ja, det er altid som det gør, at det er altid en lille smule ting, som ødelægger det hele.
Ja.
Så det er altid så mange lille ting. Ja, fint. Ja, fint. So the last thing I want to comment on. So we got this, we got that. I've posted the opgave 4, and just want to throw this up. Yeah. And so here we go. Come on. Come on. Yeah. All right. So everything you need to know to do this is last week and this week. So this is all directly out of the slides, directly out of the, I mean, and the textbook as well, but this is all directly out of last week and this week's lecture. And the data set is up there. And it's just pretty straightforward, bang, 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 answer these questions. I hope it's pretty clear. And then I'll finally get to grading your other stuff. I haven't done it yet. I need to grade your stuff from last week. I will get to that soon in the next couple of days. But this one is just, you know, straight from what we've done here in the lecture. So that's why it's important that you follow along with R and have that all figured out. But otherwise, it shouldn't be too tough. I don't think it should be. Just want to check that you can do this, that you got the skills to do this. And then that brings us, you know, pretty much to the end. But like I said, so that's it. That's it for today. But if there is something we can do to make this last week interesting or more relevant to you, or produce some value for something you're doing, please let me know. Because we have the flexibility. I can certainly add something or modify something or do something to make it relevant to something you're working on. So, but if I don't, yeah.
The exam, will that be multiple choice, or will it be like the homework assignments, or what is your plans with the exam?
The exam is half multiple choice and half essay. So there'll be
essay is like the homework assignment. So we have to work on R studio or R, or is it like write?
The plan is that it'd probably be 20 questions multiple choice, like the midterm. And then there'll be an essay, and the essay will be possibly with some calculation, like, okay, here's a spreadsheet with some data, do something with this. But more discussion, more like, okay, here is some results. Tell me what you think about these results. Explain to me what's in these results. What decision would you make? What would you do with these results? I mean, just like in the homework right now that I'm giving you, question 5 and question 6 have a discussion component to that. They're like, what do you think you should do? What, you know.
Stephen, det tekstspørgsmål. Altså når du siger essay, så det tekstspørgsmål.
Yeah, text. Yeah, det er tekstsvar, kortsvar, eller ikke så kort, men
yes.
Yeah, en lille digte. Digtesvar, eller kortsvar, yeah. En halvtreds år, måske, yeah. Yeah. But, you know, beskriv hvad har sket, beskriv hvad du kan se her i den her tegning. Forklare hvordan du tror du skal gå videre med den her resultater. Forklare hvad beslutning du synes er bedst at tage på den her tidspunkt med den her resultater, og det kan være at det er flere muligheder, og det er ikke klart at det er en som er det bedste. Det kan være god eller dårlig årsag til hver, så at man skal bare sige, ja, den her har de her fordele og ulemper, og den her har også fordele og ulemper, så Så det giver mening et tekstsvar, en tekst essay eller kortsvar. Ja. Ja, okay. Så det var det hele. Så vi ses. Nyd solen i weekenden, og vi ser frem til mere og mere varmt vejr. Så yes. And there's, come on, where is it? Where'd you go? It disappeared. Yes. Yeah, vi ses. Hi.